writing down a few things that we know from this problem is that we have a solid sphere of uniform density, I imagine, and the sphere is not slipping while it's rolling down a leveled lane. What we want to find is, I'm going to define it as P. We want to define P, which is the ratio of translational kinetic energy to its total kinetic energy. Now, the wording of the problem was, what percentage of the ball's total kinetic energy is translational kinetic energy? So that's the ratio of translational kinetic energy to its total kinetic energy times 100%. So since we're dealing with kinetic energies, I'm going to go ahead and use what I have in my physics toolbox. And it looks like the conservation of energy is probably the best bet. Since the ball is on leveled ground, we don't really care about gravitational potential energy. And it looks like we just care about the kinetic energy part. At the same time, the ball is rolling. So there's two types of kinetic energies. There's translational kinetic energy and rotational kinetic energy. Therefore, let's go ahead and write this down. 1/2 mv squared plus 1/2 I omega squared is equal to the total kinetic energy, Ke, where this part here is Ke translational, and this part here is Ke, and I'll just say rotational R. So what we're trying to find with P is 100 times 1/2 mv squared divided by the total kinetic energy, which includes the kinetic energy translational plus the kinetic energy rotational. And there you go. Next thing I want to know is, let's try to define a few things. Well, we know what I don't think we really, m is kind of like a base value. So we got that. Velocity is kind of a base value. But I kind of want to try to get these in terms of these base values. By base, I mean the linear versions of the values. It makes it easier for me to look at. So I want to try to get I and omega in terms of m and v. Best bet I have is to at least break down I for a solid sphere. And to do that, I look up on the internet for a solid sphere. What is the moment of inertia? Moment of inertia equation is 2/5 mass of the sphere times the radius of the sphere squared. I'm going to be a little worried because I'm introducing a new variable r, but let's rest assured that this will eventually phase out. So now P is going to equal to 100 times 1/2 mv squared divided by 1/2 mv squared plus 1/2 times 2/5 mr squared times omega squared. It looks a little messy, but the good thing is I got m's here. And I don't have any v's yet. Well, fortunately for me, looking at how a ball rolls, this being r, this being omega. Actually, omega points up, so I'm gonna not to confuse you. Omega will point towards you, and v will point. It looks like this way. Okay, so the equation that relates v and omega is v equals to r cross omega. I actually meant to say v is equal to omega cross r. So let's just make sure that we are okay with using this equation. Omega points up, r points down, and using the right-hand rule, v is going to point to the right. And this all works out, and they look like they're all perpendicular to one another. R points this way, v points this way, omega points upward. So we can simply say that the scalar versions of v is simply omega r. So if we have omega squared r squared, which is the same as omega r quantity squared, then this actually ends up becoming v squared. So now let's write this down. We have P equaling to 100% times 1/2 mv squared over 1/2 mv squared plus, let's go ahead and consolidate the coefficients here, 2/10 m. And now r squared omega squared is just v squared. We got ourselves a nice little equation we can simplify. So m's cross off. These squares now cross off. And we're left with just a bunch of coefficients. 1/2 divided by 1/2 plus 2/10. I'm going to go ahead and solve this out algebraically. Best thing to do is try to get the denominator in terms of their common denominators. So that's going to be 100 times 1/2 divided by, in this case, I think this is going to be 2/10. No, sorry, 5/10 plus 2/10. And that's going to come up to 7/10. And then to consolidate this here, if you have a fraction divided by a fraction, you take the bottom fraction, flip it over, and multiply it by the top fraction. So this ends up being then 100% times 1/2 times 10/7. And finally, we have 10/14, which is the same as 5/7. 100% times 5/7 comes out to be 71%. So let's kind of recap what we got here. Essentially, we are trying to find the ratio of the translational kinetic energy to the full kinetic energy of a rolling solid spherical ball. That comes out to be this equation here in its base form. Just doing a little bit of a few conversions from one variable to another in rotational mechanics, we were able to cross off basically every variable in a term, leaving only numerical ratios. And this came out to be 71%. So 71% of a rolling bowling ball, regardless of its mass, as long as it's uniform in density, will be translational. And that means that only 29% will be rotational kinetic energy.